Aloha and welcome. In this video, we're going to talk about boot integrity. So an endpoint should be securely booted to prevent the installation of malware on the endpoint before an operating system is loaded on the endpoint. That's going to happen between when you press the start button on your computer, and when it loads the operating system. That time period, we want to make sure that we're going to be securely booting the system. So we have something that allows us to do that. It's called the Unified Extensible Firmware Interface. A lot of people just call it UEFI. So UEFI is a specification that defines a software interface between an operating system and a platform firmware. So between the firmware and the operating system like Windows or whatever you have on there, you've got this UEFI. It's kind of like BIOS of the old days. If anybody knew what BIOS was, BIOS stood for the basic input-output system, and that allowed you to set a lot of things. You could set like the clock speed. You could set the date and time of your computer. You could set your boot order. You could set different information about your hardware, like your disks, your floppy disks, things like that. UEFI it's a modern version of that. It's a lot different. Instead of being a text-based system, it's actually more graphical. It's a little bit sleeker. It allows you to use mice and other your keyboard and mouse, much differently from the old system where you couldn't use the mouse. So it's got some features like that, but it also has this feature where it allows you to do a secure boot process. And that's really what we're focusing on here because we want to make sure that we're securely booting up our system. So UEFI, it has an interface that contains data tables with the platform related information and a boot and runtime service calls available to the bootloader and the operating system. So bootloader, or what we call a bootstrap loader, is a program that loads an operating system into the computer memory. And as I mentioned earlier, this is replacing the old BIOS system that we had in place. And BIOS was a program that stored non-volatile memory that performs startup procedures when the computer is powered on. We called it POST, which stood for the power on self-test, which is where you're going to go out and test the different hardware components before you start the whole system. Make sure that everything's running before you go into the operating system. Um, Also, with the unified extensible firmware interface functions, you've got some things in there. You're going to have the nice thing about UEFI compared to BIOS is it gives you the security features that you need. It also allows your system to boot up faster, and it supports a graphical user interface and mice for pre-boot configuration. So the networking features also allow it to have remote configuration, diagnostics, and troubleshooting of computers. So the UEFI initializes system hardware, detects the connected peripherals, and locates and executes a bootloader to load an operating system into memory. So UEFI can be loaded from a hard disk or a solid state drive, non-volatile memory like on the chips, or network share. And we have a good graphic it's a good participation activity that shows you the actual process that it goes through. We also talk about boot integrity. So UEFI provides security features that support the boot integrity. You're going to have two different methods here. One is called secure boot, and secure boot is a boot method that ensures only programs trusted by the system manufacturer are loaded and executed during the boot process. So a system that supports secure boot maintains the signature database of valid programs, and it's only going to execute a boot program that has a valid signature. So the signature database, it's going to be updated by the system manufacturer, and it's supported by Windows Server, Windows 10, and various Linux distributions as well. You've got another type of boot integrity method called measured boot. This is a little bit different because this one's going to use hashes, our favorite integrity checker hashes here. So it's going to hash each boot program. It's going to compute that, and it's going to store that in a trusted platform module, the TPM hardware module that modern computers have. Then we have something called the boot attestation, and that's the process of sending the measured boot logs stored in the TPM to a remote administrative server for evaluation. So the administrative server compares the software hashes to in the boot chain with the hash of a valid boot program. If a hash does not match, then the administrative server may restrict the system's access to resources or take remedial actions to secure the system. So you can use both secure boot and measure boot together to improve the security of the boot process. The next thing we're going to talk about is the root of trust. So you've got something called a root of trust, HRoT, with a small o in it. That's a system set of highly reliable hardware, firmware, and software components that perform critical security functions. So you've got a hardware root of trust, and that's where you've got the root of trust that's implemented in hardware only. So it's based on hardware validated boot process that ensures the system is started using immutable. Immutable means unchangeable code. If you've ever worked in Python, you know about mutable versus unmutable. But it started using immutable, non-changeable code that is not affected by malware. So a root of trust anchors a chain of trust that is the foundation of all secure operations of a system. In a chain of trust, the signature of each piece of firmware is validated before the firmware is executed. Upon the execution of all validated firmware, system control is then handed over to the UEFI's secure boot process. So we need to also talk about hardware vulnerabilities. Hardware vulnerabilities, including those present in firmware, pose significant risks to endpoint security. So as we mentioned before, outdated firmware that contains known vulnerabilities, those can be exploited. So when you're looking at systems, particularly ones that are using outdated hardware, you really have to think about, okay, how do we mitigate risk here? And one of the ways you mitigate risk, as we talked about before, you can take compensating measures to isolate these so that they're more secure just because you can't access them directly. Or you could do things like, it may be just time to replace the hardware if it's at end of life. You know, if you've gotten to a point where the system's so old, it doesn't have the computing power to do modern encryption, then maybe it's time to actually buy new equipment there. So you need to make sure that when you've got legacy equipment like that, you need to make sure that it's got the latest updates on it. And if those updates are just too far gone, it may be time to look at the hardware lifecycle and just say, okay, we've got to replace this hardware. So anyway, that's it for this section. If you have any questions, feel free to reach out. I'd be happy to help you with this. Just give me a call. Aloha.